when extending an existing branch circuit that lacks an equipment grounding conductor, following section 250.130c of the National Electrical Code, or NEC, is crucial. Let's clarify the interpretation of 250.130 cone and its implications for attaching the grounding electrode conductor from the new section of the circuit to the building's water piping system. It's essential to understand the relationship between equipment grounding conductors, grounding electrode conductors, and the water piping system as a grounding electrode. The short answer is no. You cannot attach the equipment grounding conductor from the new section of the circuit to the building's water piping system at the closest location. According to the 2020 National Electrical Code, section 250.130 cone specifically addresses extending existing branch circuits lacking an equipment grounding conductor. It mandates that the equipment grounding conductor for the extension shall be connected to the grounding electrode conductor at any accessible point within the first 6 feet of the branch circuit at the point of entrance to the building or structure. Now let's consider section 250.52a, which pertains to the grounding electrode system and the use of metal water piping. It states that the grounding electrode conductor shall be connected to the metal water piping system at the point of entrance to the building or structure. It's important to differentiate between the equipment grounding conductor and the grounding electrode conductor. The equipment grounding conductor's role is to provide a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices like circuit breakers or fuses. The grounding electrode conductor, on the other hand, connects the grounding electrode system, such as the water pipe, to the electrical system's grounded conductor, typically the neutral, at the service equipment. Given these requirements, the equipment grounding conductor from the branch circuit extension must be connected to the grounding electrode conductor within the specified 6-foot distance from the point of entrance of the branch circuit. This implies that connecting it directly to the water piping system at a location farther than 6 feet from the branch circuit's entry point is not permitted by the NEC. The intention behind this rule is to ensure that the equipment grounding conductor is effectively connected to the grounding electrode system, providing a reliable path for fault current. Allowing connections at arbitrary points in the water piping system could compromise the effectiveness of the grounding path and increase the risk of electrical shock. To reiterate, the equipment grounding conductor of the extended branch circuit must be connected to the grounding electrode conductor within 6 feet of the branch circuit's entry point into the building. This connection point must be accessible. This requirement ensures a reliable and code-compliant grounding path for the extended circuit. Here's a more detailed explanation broken down into key aspects to consider. Firstly, understanding the difference between equipment grounding conductors and grounding electrode conductors is vital. Equipment grounding conductors, or EGCs, are designed to provide a low impedance path for fault currents, ensuring that overcurrent protection devices, such as circuit breakers or fuses, operate quickly to clear a fault. These conductors connect non-current carrying metal parts of equipment, raceways, and enclosures to the system grounded conductor or to the grounding electrode conductor. The grounding electrode conductor, or GEC, connects the electrical system's grounded conductor, typically the neutral, to the grounding electrode system. The grounding electrode system can consist of various electrodes, including metal water pipes, ground rods, ground rings, and building steel. Secondly, NEC section 250.130c provides specific rules for extending existing branch circuits that do not have an equipment grounding conductor. This situation often arises in older installations where equipment grounding was not initially required. The NEC recognizes that simply adding an equipment grounding conductor to the new portion of the circuit without properly connecting it back to the grounding system can create a potential hazard. The extension could become energized without a reliable fault current path, increasing the risk of electrical shock. Thirdly, section 250.130 code dictates where the equipment grounding conductor of the extension must be connected. It states that the EGC shall be connected to any of the following: 1. The equipment grounding conductor of another branch circuit. 2. The grounding electrode conductor. 3. The grounding electrode. The connection to the grounding electrode conductor must be within the specified 6-foot distance from the point where the branch circuit enters the building or structure. This requirement ensures that the extended circuit has a direct and effective connection to the building's grounding system. Fourthly, NEC Section 250.52a addresses the use of metal water pipes as grounding electrodes. It mandates that if a metal water pipe is used as a grounding electrode, the connection of the grounding electrode conductor must be made within 5 feet of the point where the water pipe enters the building. There must also be a bonding jumper around any insulated joints in the water pipe. This requirement aims to ensure that the water pipe provides a reliable grounding path and that any interruptions in the pipe's conductivity are bypassed. Fifthly, the scenario in this query involves extending a branch circuit without an existing equipment grounding conductor and considering connecting the extensions EGC to the water pipe at a point beyond the 6-foot limit specified in 250.130 Code. This is not permitted by the NEC. The code specifically requires the connection to be made to the grounding electrode conductor within that 6-foot zone. Connecting to the water pipe further away would not provide the same level of protection and could compromise the effectiveness of the grounding system. Sixthly, the reason for the specific 6-foot rule is to maintain a direct and low impedance path to the grounding electrode system. The closer the connection point is to the grounding electrode, the more effective the grounding system will be in clearing fault currents and minimizing voltage rise on metal parts. Connecting further away introduces additional impedance, which can hinder the performance of the grounding system. Seventhly, consider the practical implications of this rule. When extending a branch circuit without an EGC, one must carefully locate the point where the branch circuit enters the building and identify the grounding electrode conductor. Within 6 feet of that entry point, an accessible location must be found to connect the extensions EGC to the grounding electrode conductor. This might involve running a new conductor back to the service equipment or to a junction box where the grounding electrode conductor is accessible. Eighthly, it is important to note that the NEC does allow for some flexibility in certain situations. For example, if it is not possible to make the connection within 6 feet, the code permits connecting to the grounding electrode at a different location, such as at the service equipment. However, this would typically require running a separate grounding conductor back to the service equipment, which might not be practical in all cases. Ninthly, it is always recommended to consult with a qualified electrical inspector or engineer to ensure that the installation complies with all applicable codes and standards. Electrical codes can be complex and vary depending on the jurisdiction. A qualified professional can provide guidance and ensure that the installation is safe and code compliant. Tenthly, in summary, when extending a branch circuit without an equipment grounding conductor, the NEC requires that the extensions EGC be connected to the grounding electrode conductor within 6 feet of the branch circuit's entry point into the building. Connecting to the water pipe at a location beyond this limit is not permitted. This rule is designed to ensure a reliable and effective grounding path for the extended circuit. Here are some additional considerations to further enhance understanding. Firstly, let's elaborate on the concept of impedance in grounding systems. Impedance is the total opposition to current flow in an alternating current, or AC, circuit. It includes both resistance and reactance. In grounding systems, minimizing impedance is crucial for ensuring that fault currents can quickly and effectively return to the source, allowing overcurrent protective devices to operate. Secondly, a 6-foot rule in 250.130 Code is intended to minimize impedance by keeping the length of the grounding conductor as short as possible. A longer conductor introduces more resistance and reactance, which can impede the flow of fault current. By requiring the connection to be made within 6 feet of the branch circuit's entry point, the code helps to ensure that the grounding path remains low impedance. Thirdly, it's important to understand that the grounding electrode conductor itself must also be properly sized and installed. The size of the grounding electrode conductor is based on the size of the service entrance conductor as specified in NEC Table 250.66. The conductor must be large enough to safely carry the maximum fault current that could occur on the system. Fourthly, in addition to the grounding electrode conductor, the grounding electrode itself must also be effective. A metal water pipe, for example, must be in direct contact with the earth for at least 10 feet to be considered an effective grounding electrode. Ground rods must be driven deep enough into the earth to provide a low resistance connection. Fifthly, it's also important to consider the potential for corrosion in grounding systems. Metal components that are buried in the earth or exposed to moisture can corrode over time, which can increase the resistance of the grounding path. To prevent corrosion, it's recommended to use corrosion-resistant materials such as copper or stainless steel for grounding electrodes and conductors. Sixthly, regular inspection and testing of grounding systems are essential to ensure that they remain effective. Ground resistance testing can be performed to measure the resistance of the grounding electrode to earth. This testing can help to identify potential problems such as corrosion or loose connections before they become a safety hazard. Seventhly, when extending a branch circuit without an equipment grounding conductor, it's also important to consider the type of equipment that will be connected to the circuit. Some equipment, such as computers and electronic devices, are particularly sensitive to voltage fluctuations and electrical noise. In these cases, it might be necessary to install a dedicated equipment grounding conductor to provide a clean and stable ground reference. Eighthly, in some cases, it might be necessary to install a new grounding electrode system to ensure that the grounding system is adequate. This might be required if the existing grounding electrode is inadequate or if the soil conditions are not conducive to effective grounding. Ninthly, it's also important to consider the bonding requirements of the NEC. Bonding is the process of connecting all metal parts of the electrical system together to create a common ground potential. This helps to minimize voltage differences between metal parts, which can reduce the risk of electrical shock. Tenthly, the NEC provides specific requirements for bonding different types of equipment and systems. These requirements must be followed to ensure that the electrical system is safe and code compliant. Finally, remember that electrical work can be dangerous and should only be performed by qualified individuals. Always follow all applicable codes and standards and take all necessary safety precautions. If you are not comfortable working with electricity, hire a qualified electrician to perform the work. Furthermore, let's delve deeper into the practical application of these rules and explore some common scenarios that electricians might encounter. Firstly, consider a situation where an electrician is extending a branch circuit in an older home that was originally wired without equipment grounding conductors. The electrician needs to add a new receptacle to the circuit to power a new appliance. The electrician identifies the point where the branch circuit enters the building and locates the grounding electrode conductor, which is connected to a metal water pipe. The electrician measures the distance from the entry point to the grounding electrode conductor and finds that it is within 6 feet. The electrician can then connect the equipment grounding conductor of the new receptacle to the grounding electrode conductor at that location. Secondly, now consider a similar situation, but the electrician finds that the grounding electrode conductor is located more than 6 feet from the branch circuit's entry point. In this case, the electrician cannot connect the equipment grounding conductor of the new receptacle directly to the grounding electrode conductor. Instead, the electrician must run a separate grounding conductor back to the service equipment and connect it to the grounding bus. This can be more challenging, but it ensures that the new receptacle is properly grounded. Thirdly, let's explore a scenario where the electrician is extending a branch circuit in a commercial building. The building has a complex electrical system with multiple grounding electrodes, including metal water pipes, building steel, and ground rods. The electrician needs to determine which grounding electrode is the most effective and where to connect the equipment grounding conductor of the new circuit. In this case, the electrician should consult with a qualified electrical engineer to determine the best grounding strategy. The engineer can perform ground resistance testing and other measurements to determine the most effective grounding electrode and the optimal connection point. Fourthly, consider a situation where the electrician is extending a branch circuit in a building that is supplied by a generator. The generator has its own grounding system, which is separate from the building's grounding system. The electrician needs to ensure that the two grounding systems are properly connected to prevent voltage differences and ensure safety. In this case, the electrician should follow the requirements of NEC Section 250.30, which addresses the grounding of separately derived systems such as generators. The electrician must connect the generator's grounding system to the building's grounding system using a bonding jumper of the appropriate size. Fifthly, let's explore a scenario where the electrician is installing a new electrical panel in a building. The electrician needs to connect the panel to the building's grounding system. The electrician must connect the panel's grounding bus to the grounding electrode conductor using a conductor of the appropriate size. The electrician must also bond the panel to any metal water pipes or other metal structures that are located within the panel. Sixthly, consider a situation where the electrician is working on an electrical system that has been damaged by a fire or flood. The electrician needs to inspect the grounding system to ensure that it is still effective. The electrician should check for any signs of corrosion, damage, or loose connections. If the grounding system is damaged, it must be repaired or replaced before the electrical system is energized. Seventhly, let's explore a scenario where the electrician is installing a new piece of equipment that requires a dedicated equipment grounding conductor. The equipment manufacturer specifies the size and type of grounding conductor that must be used. The electrician must follow the manufacturer's instructions carefully to ensure that the equipment is properly grounded. Eighthly, consider a situation where the electrician is working on an electrical system that is located in a hazardous location, such as a gasoline station or a chemical plant. The electrician must follow special grounding requirements to prevent explosions or fires. The NEC provides specific requirements for grounding electrical systems in hazardous locations. Ninthly, let's explore a scenario where the electrician is installing a new swimming pool. The NEC provides specific requirements for grounding swimming pools to prevent electrical shock hazards. The electrician must bond all metal parts of the pool together, including the pool shell, the metal ladder, and the pump motor. The electrician must also install a ground fault circuit interrupter, or GFCI, to protect the pool's electrical circuits. Tenthly, consider a situation where the electrician is working on an electrical system that is located in an agricultural building, such as a barn or a poultry house. The NEC provides specific requirements for grounding electrical systems in agricultural buildings to prevent electrical shock hazards to livestock. The electrician must bond all metal parts of the building together and install ground fault circuit interrupters to protect the electrical circuits. By understanding these common scenarios and the applicable NEC requirements, electricians can ensure that electrical systems are properly grounded and that people and property are protected from electrical hazards. Always remember to consult the latest edition of the NEC and to seek guidance from qualified professionals when necessary. Safety should always be the top priority when working with electricity.